This is the first of several lectures introducing the basic overview of the seismic exploration method. The previous lectures have shown how oil and gas can be trapped in various kinds of traps in the earth, and now we begin to look at how the seismic reflection method can be used to detect those traps, to detect the rock structures in the earth, and allow us to estimate where there is possibly oil or gas trapped. We begin with a very simplified overview of the seismic reflection method of geophysical exploration, and then begin to look in more detail at how the seismic energy actually travels through the earth and how we go about recording seismic reflections and processing them to obtain a picture of the rock structures in the earth. The first slide illustrates the basic seismic reflection method. We see here a simple oil trap, just an anticlinal structure with oil trapped in some reservoir rock here. The basis of the seismic reflection method is to use some source of sound energy and to detect the echoes, the sound echoes, which are reflected from various layers of rock in the earth, actually reflected from the interface between two different kinds of rock. Now, if this is done at several points across a structure such as this, we can measure the travel times to a particular interface, and then, knowing the velocity of travel to that interface, we can calculate the depth of that interface below these various points on the surface, and so obtain a picture of the structure of that particular oil trap. So the basic idea then of the reflection method is firstly to measure reflection times, and then somehow to measure the velocity with which the sound travels to the reflector and back again. And this velocity can be determined from the reflection measurements themselves, in fact. And then, knowing the times and velocities, we can calculate the depth to a particular reflector. It's simply the velocity multiplied by time and divided by 2, because we're dealing with the travel path in 2 directions, to the reflector and back to the surface again. Now we'll begin to look at some of the elements of this reflection method in a little more detail. We'll look first at the sources of the sound which we use to reflect from the rock layers. For seismic exploration on land, one of the first used sources was simply dynamite. Dynamite exploded in a hole drilled a short distance below the surface. That method is still used. Probably about 50% of the seismic exploration on land still uses dynamite as the source of sound or source of energy. Another method that is gaining popularity for land exploration is the vibrosize method. And in this method, a large machine is used to vibrate the surface of the earth rather than giving a sharp impulse as you would obtain from dynamite. For seismic exploration at sea, marine exploration, dynamite was used in the past. Dynamite charges exploded just below the surface of the water, but that method is virtually obsolete now, and it's been replaced by a variety of sources, the most common of those being a device called an air gun. The air gun is really just a a valve arrangement which allows the release of a burst of compressed air just below the surface of the water. And this gives the effect of a small explosion and generates a sharp sound. Well, the sound waves then travel from the source into the earth, and they're reflected from some of the rock layers and travel back to the surface, where they're detected by a receiver. And that receiver is basically a type of microphone, especially adapted to pick up the sound vibrations in the earth rather than from the air. That converts the sound vibrations at the surface of the earth then into an electrical signal which is amplified and recorded on magnetic tape in very much the same way that a hi-fi tape recording system would work. The recordings have to be displayed visually by some method. This is usually called playing back the recordings, and they would be picked up from the magnetic tape, again amplified, and the signals fed into a device called a plotter, which is a kind of strip chart recording device which would play out the signals that were recorded from each of the receivers. Now, when a reflection arrives back at the receiver, that would produce a sharp kick or wiggle of the trace on the strip chart, and maybe another one here from the second reflector. If we had several traces from several different receivers in a situation like this, then we'd see the reflection from a particular interface occurring on each one of those traces, and here we see the reflection from a deeper interface. And since the travel time to a particular reflection point depends to some extent on the depth to that reflection point, then the position of the reflections on these traces gives a rough picture of the shape of the geological structures in the earth. Now, this picture, as it's shown here, is a very idealized one, in that we're seeing only the reflection events on the traces and nothing else. But in practice, it's not quite so ideal as that. A typical recording in a situation just shown would produce a set of traces which look more like this, where there's a great deal of unwanted noise and other kinds of reflection events on the seismic traces. So it would become very difficult to actually identify which of these events came from a particular reflector. So the data, the seismic traces, have to be processed generally by computer to try to eliminate or reduce some of the unwanted events and noise from the traces, so that the reflections from the rock layers that we want to see stand out more clearly on the seismic traces. So once again, we can generally identify the reflections that come from one particular interface between two rocks, and so obtain a picture of the geologic structures in the earth. So the basic aim of processing then, or one of the first aims, is to make the reflections visible on the display of the seismic traces. And then once the reflections are visible, we can measure the travel time of the reflections and go about calculating the depth of those particular reflectors. Well, now we begin to look at some of the elements of the seismic reflection method in more detail. And we'll begin by looking at how the sound waves, that is the seismic energy, travels through the earth, what physically happens in the Earth as the energy travels through it, and how it is reflected from the interface between two different types of rock. Well, the seismic energy which we're working with is really the same as a sound wave, except that it's traveling through the Earth rather than through the air. There are three main physical ways in which the seismic wave can travel through the Earth, and these are called firstly the P wave mode of travel. That's also sometimes called longitudinal waves or maybe compressional waves. The second type are the S waves, sometimes called transverse waves or shear waves. And the third one is a method of travel called the Rayleigh wave. A more common name for that is ground roll. And now we'll look at how those waves actually travel through the Earth. Well, beginning with the P wave, as the wave travels through the Earth, if we imagine the Earth as being made up of a series of small Earth particles, the particles in the Earth actually move as the wave travels through the Earth. So imagine then that we have a P wave traveling in this direction. The motion of a particle in the Earth, in the path of that wave, would be backwards and forwards in the direction of travel of the wave energy. That's one of the distinguishing features of the P wave, and that's why it's called a longitudinal wave. The particle motion is in the direction of travel of the wave. It's actually, for any one particular particle, it's actually a vibration backwards and forwards about a sort of rest or central position. So if we imagine a series of particles then along a line through the Earth in the direction of travel of this wave, at any particular instant in time as the wave is traveling along, some of those particles will have moved maybe a little bit in one direction and others will have moved in an opposite direction. So that at points where the particles have tended to be squeezed together, we have a situation where the pressure in the Earth has been raised. We have a compression. At points such as this, where the particles are tending to move apart in opposite directions, we have a low pressure point in the Earth, sometimes called a rarefaction. So the P wave is actually a series of alternating compressions and rarefactions in the Earth in the direction of travel of the wave. So if we plot the pressure in the Earth along this wave, we could plot it as a kind of trace like this, indicating the degree of extra pressure or lower pressure in the Earth at these various points as the wave travels along. Now the second type of wave motion was the transverse or S wave. And in this case, the distinguishing feature is that the particle motion is a vibration at right angles, or perpendicular to the direction of travel of the energy. So again, if we imagine a line of particles in the Earth as the wave travels along, then at any particular instant in time, the particles would be displaced in one direction or the other from their rest position, which would have been in a straight line. So the displacement of these Earth particles gives a kind of picture of the wave motion, just as though we had plotted out the displacement of the particles from their rest position in this way. So this is the transverse wave, and obviously it's called a transverse wave because the particle motion is transverse to the direction of travel of the wave energy. The third type of wave motion that we'll look at is the Rayleigh wave, sometimes called ground roll. Now, the Rayleigh wave is a wave motion which takes place at the surface of the Earth, and it's the type of wave with which people are probably most familiar because it's the type of wave you would get on the surface of a pool of water if a stone were dropped in, for instance. A series of ripples would spread out on the surface, and those ripples are in fact a Rayleigh wave motion. And if we just draw the portion of the surface of the water, or it could be the ground in the case of seismic exploration work, the ground motion is actually in an ellipse, so that at some points on the ground surface there would have been a slight movement upwards, and at other points a slight movement downwards. Of course, these would be the ripples that you would see spreading across the surface of the water. The amplitude of this elliptical motion decreases fairly rapidly below the surface, and in fact by the time you get to a depth which is equal to one wavelength, that is the distance between the crests of two of the ripples, the motion of the water or earth particles would almost have ceased. If you imagine something floating on the surface of the pool of the water as the ripples spread out, of course that floating object would just move up and down. It would not move along with the ripples, which is sort of visual evidence that the motion is almost purely up and down and not a motion of the water particles along in this direction. The wave travels in this direction, but the individual particles in the earth or in the water would move actually in a mostly up and down motion, a slight ellipse like this. Now, of these three types of wave motion, the energy transmitted by these waves travels at different velocities through the earth. The P wave is the fastest of the three modes, and it's actually the P waves that we deal with mostly in seismic reflection work. The S waves travel slightly more than half the velocity of the P waves, and the ground roll a little bit less than half the velocity of the P waves. The typical velocities of these waves in sedimentary rocks, that is the type of rocks in which we would generally find oil or gas, might be from a lower velocity of about 5,000 feet per second up to a maximum of about 20,000 feet per second. In igneous or volcanic rocks, in other words, the velocities would tend to be a bit faster and may go to a maximum of about 26,000 feet per second. And generally, the velocity with which these waves travel through the rocks increases with the depth of the particular rock. This is because the deeper rocks are more compressed by the weight of all the rock material above them. This extra compression increases their density, and as the density increases, the velocity with which the sound travels through those rocks tends to increase. Now, if we have some source of seismic energy in the earth, then a source of the sound waves, those waves spread out in all directions from that source. And if they were traveling with the same velocity in all directions, at some particular time after the sound was transmitted by the source, the wavefronts or the waves from the source would form a series of concentric spheres as we've indicated here. So that if this were a P wave, for example, there would be a series of alternating compressions and rarefactions forming this series of concentric spheres. And those spherical surfaces are called wavefronts. The first of those, the one which outlines the first motion of the Earth particles due to the wave, is called a leading wavefront. Now, in dealing with the theory of seismic reflections, we very often deal with things called rays rather than with wavefronts. And a ray of seismic energy is simply the energy which travels along a line which is perpendicular at all points along its path to the wavefronts. Or strictly speaking, it's perpendicular to the tangent to the wavefront at a particular point. So in the case of the spherical waves, the ray, or a particular ray, would simply be a straight line traveling out from the source. Now, if we looked at these wavefronts at a very great distance away from the source, there would be very little curvature of the wavefronts, and in fact they'd appear to be almost flat, or plane surfaces. And a wave such as this is referred to as a plane wave, and it simply means that the wavefront surfaces are flat planes rather than spheres. And again, a ray would be the energy traveling along a line which is perpendicular at all points to the wavefronts. So these are some of the concepts that are used in dealing with the theory of seismic reflections. Now, as we pointed out before, the velocity with which the wavefronts travel through the Earth tends to increase with depth. It's not a constant velocity in all directions. And this causes the wavefronts of the seismic energy traveling out from the source to be some other shape than spheres, in fact. And if we took a more real-life situation of a source, either at the surface or very near to the surface of the Earth, and looked at the wavefronts traveling out from that source, we'd see that in fact they formed something more like an elliptical shape, or a sort of egg-shaped series of wavefronts. That is because the velocity with which the energy travels increases with depth below the surface. So a ray traveling in this direction would have traveled further in a given time than a ray traveling along the surface at a slower velocity. Now, since a ray of seismic energy is simply the energy which travels along a line perpendicular to the wavefronts, if we looked at a ray that started out in this direction from the source, then since that is a line which is perpendicular to each of these wavefronts, it must form a kind of curve like this. So in fact, the rays of seismic energy in a real-life situation tend to be curved paths such as this. And perhaps the only situation where we get actual straight-line rays are the ones going vertically downwards into the Earth, such as this, or possibly the ones traveling along the surface, directly along the surface. Well, next we look at how the seismic energy is reflected from the interface between two different rocks. So we're showing here the interface between two different types of rocks. Now, we're saying they're different because they have different velocities. That means that sound energy, P waves in this case, would travel with a different velocity in this rock than they would in this rock. If we imagine a ray of seismic energy arriving at this interface in this manner, some of that seismic energy is reflected from the interface and some of it is transmitted through the interface. Now, the ray of energy arriving at the interface is usually called the incident ray, and the reflected one is simply called the reflected ray. The one which travels through is called the transmitted, or sometimes called the refracted ray. Now, if we draw a line perpendicular to the interface at the point where the ray strikes it, and look at the angles between that line and the different rays, we can draw up some rules for the reflection of this ray of energy. Now, it turns out that the angle of incidence, that is this angle between the perpendicular and the incident ray, is always equal to the angle of reflection, shown here. For the transmitted ray, you'll notice that the ray is actually bent as it travels through the interface. So